Alright, so in this video I'm gonna be explaining another important paper with the title Factor Graph Neural Network. This important paper in 2023 in JMLR. We have witnessed a surge of graph neural networks, most of which can learn powerful representations. They have resemblance to probabilistic graphical models but break free from some limitations of them. By aiming to provide expressive methods for representation learning instead of computing marginals or most likely configurations, GNNs provide flexibility in the choice of information, flowing rules while maintaining good performance. Despite their success and inspirations, they lack efficient ways to represent and learn high-order relations among variables or nodes. So we propose factor graph neural networks to effectively capture high-order relations for inference and learning. We first derive an efficient approximate sum-product loopy belief propagation inference algorithm for discrete high-order probabilistic graphical models. We then neutralize the novel message passing scheme into a factor graph neural network module by allowing richer representations of the message update rules. This facilitates both efficient inference and powerful end-to-end learning. We further show that with suitable choice of message aggregation operators, our FGNN is also able to represent max product belief propagation. So this is the structure of factor graph neural networks. The variable two-factor module is shown on the left, and the factor two variable module, which is shown on the right. So from these node features, we have factor features, and then from factor features, we have shared parameters. This is feature mapping that then we aggregate them in another factor feature. So we represent message passing updates module and unroll the inference over discrete graphical models as a computational graph. So how you update your message passing is, I will explain that it is defined using these two modules, variable to factor and factor to variable. And these modules are combined into a layer, and the layers are stacked together into an algorithm. Though the FGNN is motivated with sum product loopy propagation, we show that by using a different form of low-rank tensor representation, it is able to exactly parameterize max product belief propagation, which is widely used, approximate maximum and posterior inference. So the theoretical relationship between sum product and max product provides understanding on the representational capabilities of GNNs. The FGNN's architecture needs to be practically learnable without being trapped in a poor local minimum. So here they talk about tensor decomposition, and then they talk about graphical models and loopy belief propagation. I have a video about loopy belief propagation in the context of graphical models. So let X be the set of variables and X sub C be a subset of variables that phi of C depends on. The joint distribution can be defined like P of X. Now, we consider two main inference tasks, the marginal inference and the maximum and posterior. Then they apply this loopy belief propagation. So the max product belief propagation can be formulated using just these three relations. Now we start the derivation by writing loopy belief propagation in vectorized form and consider factor over n sub c number of variables. So we can now update the messages like this. And a tensorized way to implement equation 12 could be used to take outer product of all incoming messages, expand the dimension corresponding to dimension of the ith variable, and element-wise multiply with the tensor. And we posit that such a low-rank representation is often a good approximation of phi of c. So if you work on these equations, you see this is the new message updates for the low-rank loopy belief propagation. So this is a single aggregator of FGNN. So now they describe factor graph neural network, which is a graph neural network model based on derived low-rank loopy belief propagation equation. So the factor to variable messages are computed like this, where M is the neural network mapping feature vectors to a length k feature vector. And Q here is the neural network mapping E sub ij to a k by L matrix. Then we do matrix multiplication and aggregation. We have a new length variable feature f sub I. So similarly, the variable to factor message is the same. The same number of the same form of formulation for variable to factor messages. So the art of this paper is just this slide, that you are representing the factor variable messages and also the variable to factor messages. So variable to factor, factor to variable. So the output is the variable. And then we motivated the construction of FGNN based on low-rank sum product message updates. It's a long paper with many propositions, and then they apply it to graph matching problem.